Welcome students, so this is the third lecture on the methods of integration. We will start off with the review question. We are given that if integral sin x over sin of x negative alpha times dx is equal to a times x positive b times log of sin of x negative alpha positive c, then we are expected to find the value of a comma b. So foremost what I will do is I will start off by considering the given integral sin x over sin of x negative alpha times dx. Now what I wish to do is I would like to add negative alpha and remove the same. So in other words, I'm adding alpha, I'm taking away alpha. Now this is equivalent to the famous sin of a positive b formula, which is equal to sin a cos b positive cos a sin b. So if I were to use this formula, let me rewrite this as sin of x negative alpha a positive b divided by sin of x negative alpha times dx. So this is going to be, applying this formula, this is sin of a times b plus cos of a times sin b. So it's going to be sin alpha. So this is what we have got. This has to be divided by sin of x negative alpha times dx. I can again rewrite this as sin of x negative alpha times cos alpha times dx divided by sin of x negative alpha positive integral cos of x negative alpha times sin alpha divided by sin of x negative alpha times dx. Now cos alpha, sin alpha, they are constants, so I can take them out. So this is going to be cos alpha integral. Now clearly you can see that sin of x negative alpha and sin of x negative alpha can be cancelled, giving us dx positive. So I can take sin alpha out and this would give me cos of x negative alpha over sin of x negative alpha, that is nothing but cot of x negative alpha times dx. Now we can integrate this. Before that, what I wish to do is I would like to draw your attention to the formula that we have for cot. So this is nothing but ln of sin x positive c. I hope you know how you are getting ln of x. So let me just show you if you are not sure of that. Now I can rewrite cot x as cos x over sin x times dx. Now by substitution I can take sin x to be equal to t. If I were to differentiate, this is going to be cos x dx is equal to dt. So I'm going to substitute dt there, and for sin x it's going to be t. This is going to give me ln t, but my t is sin x. So that's how we are getting ln sin x. So what I will do, I will substitute that here. So this is going to be cos alpha, integral of dx is x positive sin alpha, integration of this is going to be ln of x negative alpha positive c. Now what I wish to do is I would like to compare this, comparing this to the given. So we are given ax positive b times ln of x negative alpha positive c. So as I mentioned to you, so whenever they give us log, it is actually log to the base e. So always remember that. So in the place of a, I got cos alpha, so this means a is equal to cos alpha, and in the place of b I got sin alpha. So b is equal to sin alpha. So this means the value of a comma b is cos alpha sine alpha, and that is a good place for us to draw the red line. So that completes this question, students. So this is just a review question. So in this particular chapter we will be learning how to handle questions of integration. Students, this is one of the review questions. We are expected to integrate integral cosecant of tan inverse of x over 1 positive x squared times dx. So what I wish to do is I would like to start off with I'm solving this by substitution technique. So this is going to be let tan inverse of x be equal to t. Now we will be differentiating both sides. So when we differentiate, this is going to give us 1 over 1 positive x squared times dx. Differential of t is dt. So this is what we've got. So in place of dx over 1 positive x squared, I'm going to have dt, and in place of tan inverse of x it's going to be t. So we got cosecant of t times dx. Now what is this? This is nothing but ln of modulus of cosecant t negative cot t. But what is t? T is nothing but so this entire outcome is going to be rewritten as cosecant of tan inverse of x negative cot of tan inverse of x plus c. So this is the final solution. Of course you can rewrite tan inverse of x in terms of cosecant, and in this case it is in terms of cot, but it is up to you. But this is a good place for us to draw the red line, and this is the solution for the question. So we are given this question, students. This is another question we will handle using the technique of substitution. It is integral e raised to the power of x of 1 positive x divided by cos of x times e raised to the power of x times differential operator dx. So foremost what I would do is I would take let x times e raised to the power of x be equal to some t. This is a standard substitution for any quantities that you come across using the t variable. So differentiating both sides, we get, I'm going to use UV technique, so it's going to be x times differential of e raised to the power of x, that's e power x, positive e raised to the power of x times differential of x, that's 1. So this has to be operated with the dx operator, and differentiation of t is going to give me dt. So clearly you can see that we can take e raised to the power of x out, and we would get x positive 1 times dx is equal to dt. This is exactly what we have got here. So I'm going to substitute that. So this is equal to, in place of the numerator I'm going to substitute dt. In place of the denominator it's going to be cos of x e raised to the power of x, that's going to be t. So this is nothing but integral 1 over cos t, right? So let's write that. So it's going to be 1 over cos t times dt. Now let me block this. And what is 1 over cos t? That's nothing but secant t. And what is integral of secant t? That is nothing but ln of secant t positive tan t, right? And what is t? That's going to be ln of secant of x times e raised to the power of x positive tan of x times e raised to the power of x positive arbitrary constant c. So this is the final solution, and this is a good place for us to draw the red line. So that completes the solution for this question, students. We'll move on to the next one. Students, now I wish to give you some general tips for substitution. Now whenever you are given questions like this, square root of a squared negative x squared, question 1. Question 2, square root of a squared positive x squared. Question 3, square root of x squared negative a squared. And question 4, square root of a squared negative x squared divided by a squared positive x squared. So you got this entire square root flowing. Now the first thing is you will have to get rid of the root first. Get rid of the square root. That's the first thing you need to do. So for that, you got some standard substitution technique that you will have to use. So for this, if you are given a question like this, the substitution that you will have to use is x is equal to a times sine theta. Of course, some of them will use x is equal to a times cos theta, but it doesn't matter. But make sure that you got a sine there or a cos there with the constant that is featuring here. So this is the substitution that you will have to follow. Now, if you are given this root of a squared positive x squared, so whenever you got a positive term, the substitution for this should be x is equal to a times tan theta. And in this case, whenever you have like this, the x variable occurring first, then the substitution should be x is equal to a times secant theta. So square root of a squared negative, this is a squared sine squared theta. I can rewrite this as square root of a squared of 1 negative sine squared theta. I can rewrite this as square root of a squared of 1 negative sine squared theta is cos squared theta. I can rewrite this as root of a squared times root of cos squared theta. Square root of a squared is a, square root of cos squared theta is cos theta. You see that how neatly we have removed the square root. And you can use the same concept, same simplicity concept that you can apply for each one of these things. So we are given square root of x squared, so this is going to be a squared negative x squared divided by a squared positive x squared, and we would be taking x squared to be equal to a squared times cos 2 theta. So this is going to be equal to square root of a squared negative a squared times cos 2 theta divided by a squared plus a squared times cos 2 theta, which is equal to square root of a squared of 1 negative cos 2 theta over a squared of 1 positive cos 2 theta, which is equal to, now we know that 1 positive cos 2 theta divided by 2 is cos square theta. So this is going to be equal to root of a square times, so we just have 1 negative, so let me write that formula, and also 1 negative cos 2 theta divided by 2 is sine square theta. So this is going to be 2 times sine squared theta divided by a squared of 1 positive cos 2 theta. This is going to be 2 times cos squared theta. So clearly you can see that these two can be cancelled. A squared can be cancelled, and you are left with square root of sine squared over cos squared, and that is nothing but root of tan squared. And that is nothing but root of tan squared theta is nothing but tan theta. So this is how we have removed the square root. So I have in mind the substitution that you will have to use in this case is x squared is equal to a squared cos 2 theta. So that is a very good substitution. So we'll move on to the next topic. Students, there are some important integral formula that you will have to know. Now the first one is integral of dx over square root of a squared negative x squared. So this is nothing but sine inverse of x over a positive c, and it is imperative that you remember these formulae. Now formula number 2 is integral dx over x squared positive a squared. This is equal to 1 over a tan inverse of x over a positive c. Formula number 3, integral dx over x times root of x squared negative a squared. This is equal to 1 over a secant inverse of x over a positive c. Formula number 4, integral dx over square root of x squared negative a squared. This is equal to ln of x positive root of x squared negative a squared positive c. Now there is simultaneously another formula for a similar integral, but the only thing is that the sign gets reverted here. Instead of negative, you got positive. So for this is going to be ln of x positive root of x squared positive a squared positive c. So all of these integrals which I have just mentioned, it is imperative that you write it in the memory, and that would not only lessen the time to solve questions, but it will also improve your efficiency. So having mentioned this, let us deal with questions. So let me just show you how we can get this equivalent integral formula. So we are given integral dx over square root of a squared negative x squared. Now what I'm going to do, I'm going to use substitution technique. So let x be equal to a times sine theta. I differentiate both sides, so this is going to be dx is equal to a times cos theta d theta. So this can be rewritten as, in place of dx, I'm going to substitute a times cos theta d theta divided by square root of a squared negative. In place of x, I'm going to be substituting a times sine theta. So that's going to be a squared times sine squared theta. So this is equal to integral. I can take a out and write this as cos theta d theta divided by square root of, I'm taking a squared out, so it's going to be 1 negative sine squared theta, which is equal to a times cos theta d theta divided by, a squared can come out, so it's going to be a here, and 1 negative sine squared theta, that's going to be cos squared theta. So we can actually cancel these a's that we have. So now this is equal to integral cos theta, square root of cos squared theta is cos theta times d theta. So cos theta can be cancelled, giving us integral d theta, which upon integration would give us theta. Now x is equal to, let me use this space here. Now x is equal to a times sine theta. So I pushing the a down, so it's going to be x over a is equal to sine theta. So from here theta is going to be, I can push the sign to the left, so it's going to be theta being equal to sine inverse of x over a. So this is a very important substitution that we will have to know. So if I were to replace for theta, this is going to be sine inverse of x over a positive c. So this is a good place for us to draw the line, and that is exactly what we've got in the formula. Integral of dx over root of a squared negative x squared is equal to sine inverse of x over a plus arbitrary constant c. So now let me show you the second formula, integral dx over x squared positive a squared. So this is formula number 2. We are given integral dx over x squared positive a squared. So what I wish to do, I would like to take, let x to be equal to a times tan theta. Now if you were to differentiate this, differentiation of x is dx, differentiation of tan theta is going to be a times secant squared theta times d theta. So this is, let me just continue here. So this is going to be equal to integral, in place of dx I'm going to substitute a times secant squared theta d theta over x, in place of x it has to be a times tan theta. So that's going to be a squared times tan squared theta positive a squared. So this can be rewritten as integral a times secant squared theta d theta. I'm taking a squared out, so it's going to be a squared of tan squared theta positive 1. Now we know our formula. We know that secant squared theta negative tan squared theta is equal to 1 and secant squared theta is equal to 1 positive tan squared theta. We know this. So if I were to substitute tan squared theta positive 1 with secant squared theta, so this is going to be, in fact I can cancel the a out, so it's going to be integral secant squared theta over tan squared theta positive 1, that's going to be secant squared theta. There is a here, so let me place that. So now if you were to get rid of the secant squared theta, then you would have 1 over a integral d theta. Integral of d theta is theta, so it's going to be 1 over a of theta. But we know that we got x is equal to a times tan theta. So what I wish to do is, I would like to push this a down, so it's going to be x over a is equal to tan theta. So theta is going to be tan inverse of x over a. So if we were to use this here, this is going to be 1 over a times tan inverse of x over a, positive arbitrary constant c, and that is a good place for us to draw the red line. Students, we are going to obtain the equivalent formula for integral dx over square root of x squared negative a squared. So foremost, what I am going to do is I am going to take this substitution, let x to be equal to a times secant theta. If you were to differentiate both sides, you get dx is equal to a times differential of secant theta is secant theta tan theta times d theta. So with this, what I will do is probably I will use a change of color. So if I were to make this substitution, this is going to be integral. In place of dx, I will be substituting a times secant theta tan theta times d theta divided by square root of, in place of x it's going to be a secant theta, so it's going to be a squared secant squared theta negative a squared. I can take a out, so it's going to be integral secant theta tan theta d theta over square root of, so a squared can go out, so that would mean I get a here, and inside is going to be secant squared theta negative 1. But as I mentioned to you, secant squared theta negative tan squared theta is equal to 1. So secant squared theta negative 1 is going to be tan squared theta. So I can clearly cancel the a out. And then this is going to give me integral secant theta tan theta. I got a d theta there. So this is going to be root of tan squared theta. If you were to take the square root, this is equal to integral secant theta tan theta divided by tan theta, and you got the operator d theta there. So tan theta can be cancelled. This is going to give me integral secant theta d theta, which is nothing but ln of secant theta plus tan theta. But let me just write that, but my x is equal to a times secant theta, so this would mean secant theta is equal to x over a. So if you were to draw the Pythagoras, so let me just draw the Pythagoras and show you. So this is 90, right? So secant theta is x over a, so that would mean my hypotenuse would be x here, and then my adjacent side would be a. So if this is x and this is a, this is going to be square root of x squared negative a squared, right? And more importantly, this is my theta. Now this is what we have got. So from here, what is tan theta? So from here, my tan theta is going to be opposite side over adjacent side. So it's going to be root of x squared negative a squared divided by a. Right? So I'm going to substitute that. So this is equal to ln of, in place of secant theta, it's x over a. In place of tan theta, it is root of x squared negative a squared divided by a. This is equal to ln of x positive root of x squared negative a squared divided by a. Right? Now we have a formula, ln of a over b. Ln of a over b, let me write that formula here. I'm going to use the space here. You know that ln of a over b is ln a minus ln b, right? So this ln of entire quantity, I'm just using modulus because I want it to be positive. So this is rewritten as ln of x positive root of x squared negative a squared negative ln of a. Now this is rewritten as ln of x positive root of x squared negative a squared positive of negative ln a. But this can be considered as a c. This entire thing is constant c. So I'm rewriting this as ln of x positive root of x squared negative a squared positive arbitrary constant c. So this is exactly what we have got. So if you were to see the formula, this is exactly what we've got, isn't it? Of course, the specification of the domain is not there. You can use parentheses, that is alright. But just for being consistent, I have used modulus sign, because logarithmic of negative values does not exist. So that is one important thing we will have to take into account. So this is the solution that we have got, and it is a good place for us to draw the red line. Students, we got a beautiful question. We are expected to integrate integral sine 2x over square root of 9 negative sine raised to the power of 4x. Of course, we got the differential operator there. So I'm going to start off with this substitution. Let sine squared x be equal to t. So differentiating both sides, this is going to give me 2 times sine x times differential of sine x is going to be cos x times dx, and differential of t is going to be dt. Now 2 times sine x cos x, this is going to be sine 2x times dx is equal to dt. So clearly we can make the substitution. Sine 2x dx can be replaced with dt. So this is going to be integral dt over square root of 9 negative. Now sine raised to the power of 4x, but this is sine squared x, so this is going to be t squared. Now I can rewrite this as dt over square root of 3 squared negative t squared. Now we know our formula. What is that? Integral dx over root of a squared negative x squared to be equal to sine inverse of x over a plus arbitrary constant c. So this is the formula that we have studied, and we have also achieved the proof of it. So using this formula, I would be rewriting this as sine inverse of t over 3. But my t is sine squared x. So this is equal to sine inverse of sine squared x over 3 positive arbitrary constant c. So this is a good place for us to draw the red line for this question. Students, we are expected to integrate this question. Integral e raised to the power of x over root of e raised to the power of 2x negative 1. Of course with the differential operator dx. So we are going to make the substitution. Let e raised to the power of x be equal to t, differentiating both sides. This would give us e raised to the power of x times dx is equal to dt. So in place of e raised to the power of x times dx, I can always substitute dt over root of e raised to the power of x is t, but I've got e raised to the power of 2x. So this is going to be t squared followed by negative 1. Now we know a formula. What is the integral dx over square root of x squared negative a squared is equal to ln of x positive root of x squared negative a squared positive c. Now I'm going to use this formula right over here. So this is going to be ln of t positive root of t squared negative 1. Now what is t? T is e raised to the power of x. So this is going to be ln of e raised to the power of x positive root of t is e raised to the power of x. We got t squared. So this is going to be e raised to the power of 2x followed by a negative 1, and then you got the arbitrary constant c. So this is a good place for us to draw the red line. So we move on to the next question, students. Students, we are given this question, integral e raised to the power of x over 4 positive e raised to the power of 2x times dx. We are supposed to integrate this. So I will make the substitution. Let e raised to the power of x be equal to t. Differentiating both sides, I will get e raised to the power of x times dx is equal to dt. So clearly e raised to the power of x times dx can be substituted with dt. So this is going to be integral dt over 4 positive e raised to the power of x is t. So this is e raised to the power of 2x. So this is going to be t squared. I'm going to rewrite this as dt over, so let me write it as t squared positive 2 squared. Now we know a similar formula. We know that integral dx over x squared positive a squared is equal to 1 over a tan inverse of x over a positive c. This formula is already known. So using this formula, this can be rewritten as, so if we were to apply this formula, we would get this to be the result, 1 over 2 tan inverse of t over 2, and substituting the value for t as e raised to the power of x would give us 1 over 2 times tan inverse of e raised to the power of x over 2 positive arbitrary constant c. So this is a good place for us to draw the red line. Students, we are going to see two new types, 1 over a quadratic equation or 1 over square root of a quadratic equation. So that integral will look like this. So dx over ax squared positive bx positive c, or you will be given integral dx over square root of ax squared positive bx positive c. So in either of these cases, what you got to do, you will have to rewrite the denominator ax squared positive bx positive c as a perfect square. So this is the key, rewriting the denominator as a perfect square. Now this is the next type. In this case, you will have a linear over a quadratic or a linear over square root of quadratic. Say for example, integral px positive q over ax squared positive bx positive c, or integral px positive q over square root of ax squared positive bx positive c. So in either of these cases, what you have to do is you will have to take the numerator and rewrite the numerator as lambda times differential of this quantity, what you see here. In this case, the quantity you see inside the square root. So that's going to be 2 times ax positive b positive mu. So rewriting the numerator, right? So that would help you to solve this question. And the better way, or the most important thing we need to know here is problems will give us a better understanding. So let's do some problems. Students, let's try applying the concepts we studied in solving this question. Integral e raised to the power of x times dx over square root of 5 negative 4 times e raised to the power of x positive e raised to the power of 2x. So we got a function which is exponential in nature. So for that, what we need to do is we need to start off with the substitution. So I'm going to say let e raised to the power of x be equal to t. Differentiating both sides, I get e raised to the power of x times dx is equal to dt. So if we were to substitute that, this is going to be, in place of e raised to the power of x dx, it's going to be dt over square root of 5 negative 4 times, in place of e raised to the power of x, it's t followed by t squared. So I'm going to rewrite this as integral dt over t squared negative 4t positive 5. Now this is algebraic, right? So this is a quadratic equation. So if you have something like this, say 1 over root of a quadratic, then I told you according to the key we need to rewrite this as a perfect square. So that's exactly what I'm going to do. So this is going to be integral dt over square root of, I'm going to split 5 as 4 positive 1. So this is going to be t squared negative 4t positive 4 positive 1. So this is one term and this is another term. Now what is this? This is t negative 2 raised to the power of 2. So this is equal to integral dt over square root of t negative 2 raised to the power of 2 followed by 1. Now we know a formula. What is that? We know that integral dx over square root of x squared positive a squared is equal to, what is that? Ln of x positive root of x squared positive a squared positive arbitrary constant c. So this is known. Now I'm going to apply that. So this is equal to ln of, in place of x I've got t negative 2. So it's going to be t negative 2 positive root of this entire term, t negative 2 raised to the power of 2 positive 1. So this is what we have got. But my t is e raised to the power of x. So this is equal to ln of e raised to the power of x negative 2 positive root of. So we have to substitute e raised to the power of x followed by negative 2 raised to the power of 2 positive 1 and positive arbitrary constant c. So this is a good place for us to draw the red line for this question. Let's do another question, students. Just for the sake of perfection, make sure to place the parenthesis here. So we are given this question. We are expected to integrate integral x times dx over x raised to the power of 4 positive x squared positive 1. Now what I'm going to do is I'm going to make the substitution. Let x squared be equal to t. So differentiating both sides, you will get 2 times x dx is equal to dt. We just have x times dx, so I will have to push this 2 down. So this would give me x times dx is equal to dt over 2. And rewriting this is going to be integral x dx, that's going to be dt over 2, I'm going to place 2 here, divided by x raised to the power of 4. Now x squared is t, so x raised to the power of 4 is going to be t squared followed by t positive 1. Now this is of the type 1 over a quadratic equation, right? This is the type that I have just shown you. So for that I need to change this into a perfect square. So how are we going to do that? Now t squared positive t positive 1, I would like to, I can't do anything with the t, but I can always manipulate this 1. Now if I were to rewrite this entire component as t positive 1 over 2 raised to the power of 2, this is going to give me, if I were to expand, I get a t squared positive 2 times t times 1 over 2, that's going to be t. So I've already got a t squared and a t, so that's fine. But if I were to square this 1 over 2, that is going to give me 1 over 4. But I will have to remove this 1 over 4. So I can place this negative 1 over 4. And this positive 1 should always be there because that's part of the question, right? So what I will do is I will rewrite t squared positive t positive 1 using this entire expression. That is, I add 1 over 4, I take away 1 over 4. That's what I need to do. So this can be rewritten as 1 over 2 integral dt over, so I'm going to add it in this fashion. So t squared positive t, nothing is done for that. So I need to add 1 over 4. So 1 over 4 is nothing but 1 over 2 raised to the power of 2. I need to get rid of that. So it's going to be negative 1 over 2 raised to the power of 2, positive 1. Now let me find out what happens when you add negative 1 over 2 raised to the power of 2 with 1. So that's going to be 1 negative 1 over 4, which is going to be 3 over 4. So that would be the value that we are getting. So I'm going to rewrite this as 1 over 2 times integral dt over, so this entire thing can be clubbed. So this is going to be t positive 1 over 2 raised to the power of 2. That's fine. And followed by positive 3 over 4. So that's perfect. So now the most important thing is that we need to split, or I should say we need to make some alterations with this 3 over 4. So I would be rewriting 3 over 4 as, so let's rewrite this integral dt over t positive 1 over 2 raised to the power of 2 positive 3 can be rewritten as root 3 followed by a 2 there, and it has to be raised to the power of 2. So this is very similar to, we know that integral dx over x squared positive a squared, right, which is nothing but 1 over a tan inverse of x over a positive c. So I'm exactly going to apply this formula over here. So if I were to do this, this is going to be 1 over 2, 1 over a, so 1 over my a is root of 3 over 2 times tan inverse of x over a. So in this case my x is t positive 1 over 2 over a, that's going to be root of 3 over 2, right? So this is what I've got. So now I need to make some simplification or perform some simplification. A 2 here and a 2 here can be cancelled. So I have 1 over root of 3 tan inverse of, this is going to be 2 times t positive 1 over 2. If I were to flip this, this is going to be, I can push this off, right? I can actually bring this over here, 2 over root of 3, like that. So clearly the 2 can be cancelled, but my t is this value, t is equal to x squared, so we'll have to substitute that value. So this is equal to 1 over root of 3 tan inverse of 2 times x squared positive 1, and I got a root 3 there, so I place the root 3 and the all important arbitrary constant c. So this is a good place for us to draw the dotted line. So that is the solution for this question. Students, we expected to integrate this question. Now closer observation would reveal to us that this is of the form linear over quadratic. So we will have to rewrite the numerator, which is 4x positive 3, as some constant times. So in this case it's going to be lambda times differential of the denominator. In this case it's going to be 6x positive 3 positive mu. Now if we were to distribute this, this is going to be 6 times lambda times x positive 3 times lambda positive mu. This is what we've got. On the left hand side it's going to be 4x positive 3. So equating the coefficients of x, we would get 6 times lambda is equal to 4. Therefore lambda is equal to 4 over 6, which is 2 over 3. So this is the value for lambda. And let me use the space here. and in this case the constant. So equating that, we get 3 times lambda positive mu is equal to 3. My lambda is 2 over 3, and this is going to be 2 positive mu is equal to 3. Therefore the value of mu will be equal to 1. So I've got the value of mu, I've got the value for lambda. So therefore the numerator, which is 4x positive 3, is rewritten as lambda times 6x positive 3 positive mu is 1. So this is how we need to rewrite the numerator. So what happens to the question? Hence integral, this is exactly what we have been given, 4x positive 3 times dx over 3 times x squared positive 3x positive 1. Now this is rewritten with this newly obtained numerator, which is 2 over 3 times 6x positive 3 positive 1 divided by 3 times x squared positive 3x positive 1. We got the differential operator dx and the integral sign. Now I am going to split this as 2 over 3 integral this quantity 6x positive 3 times dx over 3 times x squared positive 3x positive 1, that's 1, followed by the other quantity 1 times dx. So this is actually a parenthesis there. So if we were to place dx outside, that is the exact meaning of it. So this is rewritten as integral dx over 3 times x squared positive 3x positive 1. Okay, so you got two quantities. Integral 1, probably you can name it as I1 and you can name it as I2. And then you can state here, consider I1. So if I were to consider I1 is 2 over 3 integral 6x positive 3 over 3x squared positive 3x positive 1 with the differential operator dx. So what I'm going to do is I'm going to make the substitution. Let 3 times x squared positive 3x positive 1 be equal to sum t. I differentiate this, I get 6x positive 3 times dx is equal to dt. I substitute, that's going to be equal to 2 over 3. In place of 6x positive 3 times dx is going to be dt. And in place of 3x squared positive 3x positive 1 is going to be t. This is going to be 2 over 3 ln t, which is 2 over 3 ln of 3x squared positive 3x positive 1. This is what we've got, positive arbitrary constant c. This is for I1. Now let's consider I2. So let me write that down. Consider I2. So what we have got in I2, we have got integral dx over 3 times x squared positive 3x positive 1. I want to take the 3 out of the denominator. So that would give me 1 over 3 integral dx over x squared positive x positive 1 over 3. That's fine. Now I can rewrite x squared positive x positive 1 over 3 as x positive 1 over 2 raised to the power of 2. I need to get rid of that negative 1 over 2 squared along with adding the 1 over 3. So this is what we have used in one of the questions. So using that, this is rewritten as 1 over 3 integral dx over x positive 1 over 2 raised to the power of 2. I have a 1 over 3 and a 1 over 4. So let's check it out. What happens 1 over 3 negative 1 over 4. LCM is 12. This will give me 4 negative 3, which is equal to 1 over 12. Right? So I can rewrite this as this is equal to 1 over 3 times integral dx over x positive 1 over 2 raised to the power of 2 positive, I'm going to rewrite it as 1 over root of 12 raised to the power of 2, right? Because when you square this, it's going to be the quantity that we have got. Now we know that, what do we know? We know that integral dx over x squared positive a squared is 1 over a tan inverse of x over a plus c. We know this formula. I'm going to use this formula over here. So this is equal to 1 over 3. If I were to use this, 1 over a is going to be 1 over this a is going to be 1 over 12, right? So I need to place that value. So it's actually root of 12, so let's place there. Tan inverse of x is x positive 1 over 2, that's right, divided by 1 over 12. So that's going to be 1 over, it's actually root 12, 1 over a. So x positive 1 over, this can be simplified, and we need to do that simplification. So this is equal to 1 over 3. I can push this root 12 to the numerator, so that's going to be 4 times 3, right? 4 times 3 is 12. So okay, so let me just place this as root 12, and tan inverse of my x, this can be simplified. So this is going to be 2 times x positive 1 over 2. I can push this root 12 to the numerator, so that's going to be like that. Now I'm not adding this c as yet, so this is going to be, if I can simplify this, let's just retain it as it is now. So root of 12 times 3 tan inverse of 2x positive 1 divided by 2. Now this 12 is actually 2 times root 3, right? 2 times root of 3, and a 2 and a 2 can be cancelled, and if I were to cancel the 2 and a 2, this is going to give me root of 12 over 3 tan inverse of root of 3 times 2x positive 1, positive arbitrary constant c. So this is what we have got. Now the question only stops if we were to club these two together, because we started off with taking I1 and I2, right? So the final solution is going to be, this is equal to, so my first integration which we got is this, so I need to place that there. So it's going to be 2 over 3 ln of 3x squared positive 3x positive 1, followed by this quantity root of 12 over 3 tan inverse of root of 3 of 2x positive 1. Now this was obtained because we simplified this root 12, right? Of course we need to place the important arbitrary constant c, and this is a good place for us to draw the red line. Students, we are given this question, integral 5x positive 4 over square root of x squared positive 2x positive 5 times the differential operator dx. Now this is of the form linear over root of quadratic type. So for that you would have to take the numerator and rewrite it as lambda times differential of the quantity inside the square root. That's going to be 2x positive 2 positive some mu. Now if I were to rewrite this, this is going to be 2 times lambda times x positive 2 times lambda positive mu is equal to 5x positive 4. So equating both sides for the coefficient of x, I would get 5 is equal to 2 times lambda. So therefore lambda is equal to 5 over 2. And for the next constant, equating the constants, we have 2 times lambda positive mu is equal to 4. So this is 2 times of 5 over 2 positive mu is equal to 4. 2 can be cancelled. 5 positive mu is equal to 4. Therefore mu is equal to 4 negative 5, which is negative 1. So therefore the numerator 5x positive 4 is rewritten as 5 over 2 times 2x positive 2 Lambda is -1. So, I mean, mu is -1. So, we have to place that. So, this is what we have got. So, therefore, the given question, which is 5x positive 4 of over root of x squared positive 2x positive 5 times dx is rewritten as the numerator is 5 over 2 times 2x positive 2 -1 times differential operator divided by the denominator x squared positive 2x positive 5. So I can split this as two integrals. So this is equal to 5 over 2 integral 2 times x positive 2 times dx divided by square root of x squared positive 2x positive 5 negative integral dx over square root of x squared positive 2x positive 5. So we can take this as integral 1, integral 2, and then start with consider I1. So that is 5 over 2 integral 2x positive 2 times dx divided by square root of x squared positive 2x positive 5. So what I'm going to do, I'm going to take x squared positive 2x positive 5 is equal to t squared because I want to get rid of the square root. If I were to differentiate both sides, I get 2x positive 2 times dx is equal to 2 times t times dt. So I'm going to substitute that over here. So this is equal to 5 over 2 integral 2x positive 2 times dx. That is going to be equal to 2 times t dt divided by root of x squared positive 2x positive 5 is t squared. So clearly I can get rid of the 2 here, and that would give me 5 times integral t times dt. Square root of t squared is t, so I can get rid of this t, giving me 5 times integral dt. Now integral of dt is t, so it's going to be 5 times t. T squared is this, so therefore t is going to be 5 times square root of x squared positive 2x positive 5. Of course we need to place the arbitrary constant. So that is done. Now we will have to move to the other end of it. So let's do that. So I'm going to consider now I2. So this is my I2. So it's integral dx over square root of x squared positive 2x positive 5. Now x squared positive 2x positive 5, we can write it in perfect square. So the denominator can be rewritten as x positive 1 raised to the power of 2 followed by a positive 4 there, because if we were to expand this is going to give us x squared positive 2x, so first two terms, plus 1, and that one when added with 4 would give us 5. So that's neat and clear. So this is equal to integral dx over, now I'm going to rewrite this as x positive 1 raised to the power of 2 positive 2 squared. Now we know a similar integration, right? Integral dx over root of x squared positive a squared is equal to ln of x positive root of x squared positive a squared, positive arbitrary constant c. So I'm going to use this integral formula over here. So if I were to use that, this is equal to, so I need not have to place this integral sign because I'm just going to apply this formula. So let me change it into parentheses, right? So this is equal to ln of my x is going to be x positive 1 positive root of, it's going to be x the first term with the second term, right? Because that's exactly what we have to do here. So that would mean I get x positive 1 raised to the power of 2 followed by the second term. The second term is actually 2 squared. So this can be further simplified to be as ln of x positive 1 positive root of, if we were to expand this is going to give me x squared positive 2x, positive 1 added with positive 2 squared will give me positive 5 with the arbitrary constancy. So this is my I2. Now we need to club both the things, I1, so we can state here therefore I1 plus I2. So now it's time for us to club the final solution. So let me use the space over here. So this is where we started, right? So we have evaluated I1, we have evaluated I2. So now we need to sum up these two quantities. So I1, we have already obtained the value for I1. So this is the value that we have got. So let's place that. So it's going to be 5 times root of x squared positive 2x positive 5, that's 1, followed by a negative sign. That's important. So we have only taken I2, right? We have only taken I2 and we have evaluated the value for I2, and that has turned out to be, let me place the value, ln of x positive 1 positive root of x squared positive 2x positive 5, right? And we need to place the arbitrary constancy. So this is the final solution, and that is a good place for us to draw the red line. Thank you, students. We will meet in the next class.